Hi guys, welcome to Learn Electronics Repair. Today we're going to have a look at some fairly common electronic components that seem to cause quite a lot of confusion with people. I noticed in some comments that somebody posted on a recent video that they misunderstood these components, and I'm thinking, if some people misunderstand them, maybe more people misunderstand them. So the components we're going to talk about today are these ones, and they're very closely related to each other. So we have thyristor, we have triac, and we have diac. So these are the three types of components we're going to talk about. Really, in a way, they progress from each other. So we'll start with the thyristor first, and then it's fairly easy to understand the other two. And the thyristor ain't difficult, yeah. So a thyristor also has another name, which is SCR, and you'll sometimes see them called SCR, and this in itself is an abbreviation, and it stands for silicon controlled rectifier. So basically a thyristor is a diode, a rectifier diode, that you can actually control. Here is a silicon diode, a rectifier diode. And I expect you probably know that a diode will basically conduct in one direction, so it conducts current one way and it blocks current the other way. And we can see this by looking at this diode. So we have two terminals. This has the stripe on, I think you can just see it. That is the cathode and this is the anode. And if we apply voltage with a positive voltage to the anode, the diode will conduct, and it drops about half a volt across it, which means the voltage coming out is about half a volt less than the voltage going in. If we put it the other way around, it doesn't conduct at all. So that is a diode or a rectifier, and we can draw that. So here is our diode. This is the anode, this is the cathode. So the cathode is the end with the stripe on. Okay, so it's easy to remember that because the cathode is where the stripe is, or the line is in the symbol. So that is our diode. And if we put a positive voltage on this end relative to this end, so if you like plus and naught or plus and minus, current will flow. And when the current is flowing, it drops about half a volt. We've seen that with the multimeter in diode mode. That's what a multimeter in diode mode shows you, the voltage drop. So imagine we had a diode that effectively had an enable pin. So if you put voltage on the enable pin, you can switch the diode on and it will act as a diode, a rectifier, passing current in one direction. If you remove the enable signal, it will switch off. Well, that's almost how a thyristor works, but not quite. So this is the symbol for the thyristor, and it looks much like a diode. But it also has an extra connection which could be shown here or here or here. Usually the symbol is this one. It has three connections. Like before, anode cathode, which is usually with a K, but it could be with a C. Anode cathode, and this is the gate. So that is a thyristor, a controlled diode, a switched diode. But there's a little bit more to it than that. To understand how the thyristor works, it's best if I draw the equivalent circuit using transistors, and this I'm sure will give you a very clear understanding of how this actually works. So imagine we had a circuit like this. We have a load, light bulb or some other load, okay, and we connect this to a PNP transistor. I know you hate PNP transistors because they're all upside down and back to front, but we have to use one, okay. So we have a PNP transistor, This is the base. And we have another transistor. So from this point, we have the gate. Okay, and from here, it goes into the base of another transistor. This one is an NPN transistor, which are far more sensible devices. And this goes to ground. This is your positive supply. Okay, and lastly, we connect the connector of this one to the base of this one. I'll put a resistor in because we need to limit the base current. Okay. Now imagine that this is connected to ground. Okay, we can actually do that. We can put another resistor in here, and we connect it to ground, and we can put another resistor in here, and we connect this to positive with a switch. Okay. If the switch is open, then the base of this transistor is held at ground 0 volts via these two resistors. So this transistor is off. No current can flow. There's no current path, okay? Now look what happens when we switch this on. We close the switch and we put some voltage on the base. And when that voltage reaches about 0.6 volts, they're about 0.5, 0.6, 0.7 depending on the transistor. 0.6 is a good average. When it reaches 0.6 volts, some current starts to flow through this resistor, into the base and down to ground. And that will turn the transistor on. So the transistor turns on or partially on, depending on the value of these resistors, how much current we're providing. Once this transistor turns on, current will flow. Collector emitter, a larger current. Okay? And that current has to come from positive. And the way it comes is via the semiconductor junction here. Imagine a transistor inside, we've looked at them before, hopefully you saw it. Effectively looks like two diode junctions, although you can't make a transistor that way. Okay? So the current will flow into the emitter, into the base, and down into the other transistor. Okay? But because there's current flowing through the emitter into the base voltage now will be lower than the emitter voltage. Yeah, it will be lower. That's because this transistor is holding the voltage here down. So this is a PNP transistor. With the NPN transistor, you needed a positive voltage on the base to turn it on. With a PNP, we need a negative voltage on the base with respect to the emitter to turn it on. And we now have that. So when the base reaches about minus 0.6 volts relative to the emitter, notice they're all positive voltages. If this was 12 volts, this would actually be 11.4 volts. But it's still 0.6 volt negative. Don't let these negative voltages confuse you. Where do they come from in the positive circuit? Yeah, we have 0.6 volts less here than we have there. So this transistor turns on. Where does the current go? It goes through the transistor and it goes into the base of this one. Okay, that now provides even more base current. So this turns on harder, pulling more current through this junction, turning this one harder. So as near as damn it, instantly both these transistors will switch fully on and they'll be fully conducting. This one is providing the base current for this one, and this one is drawing the base current for that one. What happens now if you open the switch? Well, there's no voltage here anymore. Will the transistor switch off? No, because this transistor is now providing the base current. This is effectively like a latching circuit. Once it switches on, it latches on. If you want to think of it in another sense, this is a form of positive feedback. So once some current starts to flow, it causes more current to start to flow, which causes more current to start to flow. That's the positive feedback, yeah? Just think of it as a latching circuit. So we switch it off and this stays switched on. And if there's loads of light bulb, it's still glowing. So how do we switch the light bulb off? Well, there's only one way we can switch the light bulb off. And that's to put a switch in here and break the main circuit flow, the main current flow. Then it will switch off. And now it'll stay switched off until we put some voltage back on here and it'll switch on and latch again. That is what a thyristor does. From this then, we've learned a few important things. The gate voltage required to turn the thyristor on is roughly equivalent to the base emitter voltage of a transistor, about 0.6, 0.7 volts. Okay? Was equivalent to that. It's actually the current that switches it on, so we need to put a resistor in here to prevent an excessive current flowing and effectively destroying that junction. That's the second thing we've learned. I said, and it's true, that when you open this switch, this will stop conducting. But there's actually another way that this can switch off. And that is that if the load here is high enough resistance so that the current is too small to make this latch, it will switch off. So a thyristor has some important specifications if you look at the data sheet, and they are the most important ones. The maximum voltage, how big a voltage can we put across here? Yeah. The maximum current, voltage max, current max, yeah, the maximum current. How much current can flow through here? The third one is the wattage, how much power it can dissipate, because when you have voltage across the device and current flowing through it, it will generate heat, wattage, yeah? So we have the maximum wattage. Then we have two more important ones. We have the gate threshold, which is actually in milliamps or microamps, milliamps. How much current do you have to start flowing through here to start this avalanche effect of it switching on and staying on? That's the threshold. Some thyristors are more sensitive than others, so we have that. And the last one we have is a latching current. Which is normally in amps. Okay, this is when you switch it on here, how much current needs to flow through this to cause it to latch. If that current is too low, when you switch off, it will switch back off again. So those are the main parameters that you will find on the data sheet, and if you're selecting a thyristor, those are the important ones. Normally speaking, voltage of thyristors is 400 volt because they're usually mains switching devices, don't have to be. The current will be in amps, usually, yes, small ones in milliamps, but usually in amps, and often in high currents, 10, 20 amps more. The wattage is normally very low because when a thyristor is switched on, the voltage drop across it is extremely low. The wattage, voltage times current, because the voltage drop across is very low, the wattage is very low. When the thyristor is switched off, there's no current flowing, so the wattage is zero. So the wattage we actually see is not the wattage of the device, it's the wattage of the gate, because there's a certain amount of voltage drop here, 0.6 for a volt. Yeah, so you'll see the wattage quoted on a thyristor, but it's actually the wattage dissipated in the gate circuit. It will actually usually be called the gate dissipation, and it's typically so many milliamps, 100 milliamps, a few hundred milliamps, an amp or something. Yeah. So that's how the thyristor is specified. Thyristors are usually high-powered devices, but they can be quite small. They can look like a transistor. For example, this one, PCR406, typical small SCR or thyristor, and it looks basically the same as a transistor. If we look at some of the ratings, we can see here we have the repetitive peak off-state voltage. This is effectively the voltage the thyristor can withstand. 400 volts is typical, 600, 800, 1000 are very common. As I mentioned, we will have the on-state current. This is the maximum current it can provide. The average on-state current for a half cycle, half an amp on this one. You cannot apply a negative voltage to try to switch the thyristor on with respect of the cathode, gate to cathode, so that's the maximum voltage. Gate current, I mentioned, 100 milliamps. Gauge dissipation, this is the only way that wattage applies to these, as I mentioned, 150 milliwatts. That's a fairly typical one. The other things I mentioned were the gate trigger voltage, 0.8 of a volt on this one. The trigger current, extremely small, 200 microamps. And we have the latching current here, yeah, 6 milliamps. This is the current, minimum current that needs to flow between the anode and cathode for it to latch on, otherwise it will switch off. So those are the main parameters really you would be looking for on a datasheet if you want to replace a thyristor but you don't have any of the original type. There is a very common misconception that thyristors and triacs can only switch AC voltage. That isn't correct at all. They quite happily switch DC voltage. The reason for this belief that they are AC switches is because generally that is where they're used, and I'll explain why. Let's have a quick look at a basic thyristor circuit. Here is our thyristor. Our load, our supply, and our ground or negative 0 volts. Usually a thyristor is used to control AC, and the reason being is this. We have live, neutral, AC voltage, 220 volt light bulb, and in here you can put a resistor with some sort of switch, which could be a transistor or something similar to here, and here another resistor to ground. Now coming in is AC, but the thyristor only conducts in one direction. It only conducts half cycles. So if we switch this on, the thyristor will conduct, but the lamp will come on at half brightness, and the reason being because it's only conducting half cycles, 50% of the power basically. So you sometimes find these wired in this way, where you will have a bridge rectifier, AC, AC, plus minus. We can put our mains in here, and only the positive half cycles come out of here. So effectively this is AC, and coming out here is actually twice the frequency, lots of positive cycles. It inverts the negative half cycle basically. So we have that. Now when we close the switch, this will turn on. When we open the switch, it will stay turned on as I just described, but only until the input voltage comes to 0, or more technically speaking, the threshold current is not reached. The current flowing drops below the threshold. It will then switch off, and it'll stay switched on until we close the switch again. It'll switch on again. So this is now acting like the enable signal. and it's doing so because we have a pulsed DC voltage coming in. Now a thyristor can conduct AC in one direction, and you'll sometimes find the circuit like this. So we have, again, the load, the thyristor, okay, live, neutral. Notice there's no bridge rectifier now. This is AC. I wish I could draw a little bit better for AC than that. There you go. This is AC. And we have the gate. We still have the two resistors in the switch. Switch it on. Resistor. Switch. The other resistor. But the thyristor will only turn on when there's a positive voltage on the gate with respect to this end, the cathode, okay? If you put too much negative voltage on the gate, you will actually destroy the thyristor. So what we do is, from here, quite simply, we put a diode. So when the AC goes positive and the switch is closed, we get voltage on here, it switches on. When it goes negative, this won't conduct, the lamp is now off on the negative half cycle, and this diode stops a negative voltage getting onto the gate. So that's why we do that. Those are basic thyristor circuits. We can do better things than that with a thyristor. You know now it conducts in the positive half cycle, and it doesn't conduct in the negative half cycle, okay? Conducts in the positive half cycle. So if we have a switch here, just a switch, and we close the switch, or a transistor and we turn it on, what you will get coming out is that. All the positive half cycles, okay? No bridge rectifier, so you won't get the full wave rectified, just half of them, half brightness lamp. Now what we can do is replace the switch with a control circuit, and the control circuit can monitor the voltage of the waveform, okay? If we, for example, have a control circuit that monitors this voltage, and when it reaches its peak, it switches the thyristor on, what we will get coming out, effectively, I'll draw it again so it'll get a bit messy, we'll get just that part of the half cycle, okay? That. If we turn it on when it's crossing 0, so we detect the AC is at 0, we'll get the full half cycle. If we switch it on at this point, we will get more. Yeah, we'll get a wider piece here, so it will actually also have, where's my other coloured pen? Switch it on here, it'll actually have that waveform. 3/4 of it now, yeah? And if we switch it on over here, we will get just a very narrow bit. So it's mostly off. As you can see, this will make quite a nice light dimmer, apart from the light bulb can only ever go on at half brightness. You don't have to maintain a voltage on the gate, like for example with the transistor, you have to put a voltage on the gate and leave it there all the time the transistor is switched on, otherwise it will switch off. As I explained with the Triac, once you apply voltage to the gate, it will turn on and you can remove the voltage, it will stay turned on. And the voltage, actually, you only need to apply it for a very short period of time, milliseconds, microseconds maybe. So to turn these circuits on as I was describing, you just send a pulse. So you'd normally use a microcontroller or something similar, and you'd send a pulse. So if we detect the point where the voltage passes 0, and this is your gate, so on the gate we just put a small pulse, 0.6, 0.7 volts. Normally you would use a resistor anyway to limit the current. It will turn on. The next time you need to turn it on If you try to turn it on during the negative half cycle, nothing will happen. As the voltage passes 0 again, so this is the 0 passing point, we can detect that and we can send another pulse. Very short duration pulse, low voltage, and that's how you control the thyristor. And you can see if you move the pulse up or down, sideways, it's almost like a sort of pulse width modulation, but you're not actually modulating the width of the pulse you send. It's the natural behaviour of the thyristor to switch off when the main current stops flowing that eventually switches it back off again. Okay, so it's not really pulse width modulation, but you can vary the output. For example, you can make the light bulb dimmer or brighter just by moving the position of the pulse with relation to the 0 crossing point. As you can see then, it is easy to control a thyristor to effectively control the voltage output to the load, or at least the average voltage to the load. But there's an important thing you probably do realise about this circuit, and that is that when you apply the voltage to the gate, it's with reference to the cathode, and the cathode is connected to the neutral of your mains, and the other end, by the way, is connected to the live. So the thyristor is part of the high voltage circuit, the live circuit. This, if you like, is hot ground. Now normally the control circuit would be something like a microcontroller or something similar, which is on safety ground, and you can't connect the safety ground of your microcontroller, your Arduino or whatever the chip is, microcontroller. You can't use this effectively to send a signal into the gate of your thyristor. And the reason being, as I mentioned, that this end is hot ground. Your microcontroller is going to be connected to safety ground, and you can't connect safety ground to hot ground for reasons of A, things will blow up, and B, things will become live. So we need to get around this, and this is probably true in most of the thyristor circuits you will find. There are some cases where the controller is also live effectively, or not live, but it's with reference to hot ground. So to get around this, we use an opto-isolator. I'm sure you've seen opto-isolators. You have your controller, can't fit it on one line, controller connected to safety ground, and this connects to an opto-isolator. So your opto-isolator inside has a LED, usually an infrared LED, and the other end of the LED you can now connect to the safety ground, and when you put voltage on here, this will light up, and it shines on the base of a phototransistor. So a phototransistor is like a normal transistor, but instead of having to put voltage onto the base to switch it on, you just shine a light on it, and by shining a light on it, switches on. The phototransistor can now drive your thyristor, which is almost going off the page, just so happens, but it's fitted. That was obviously planned and designed, it didn't happen by random. Okay, and the phototransistor now, this can connect to hot ground, and the anode of our thyristor can connect to hot ground. So the voltage on the gate now is with reference to hot ground, and that works. You now have the low voltage circuit isolated from the high voltage circuit. Also, you probably want to monitor the 0 crossing point. So what you will do is, this is effectively the other side of the load, this is your live, this is AC. You will have from here a resistor to another opto-isolator, okay, wired the other way around. So this is hot ground, resistor in there, this is the LED, Okay. And inside the opto isolator is the photo transistor, another one. The emitter can send the signal to our controller, and the collector can now connect to our low voltage supply, 5 volts or whatever the logic's running on. So we'll probably have a resistor in here, but you can do that, and you can see that this one is driving the thyristor, okay, and this one is monitoring the zero crossing. So as the AC comes through 0, the LED goes out. This says, the LED's gone off, I'm on 0, and it can now either switch this on instantly to get the full cycle, or it can count a certain number of milliseconds or microseconds and then switch it on. And that's how you control the phase, this kind of pseudo pulse width. Yeah, so this is a very common circuit you'll find, but you won't find it quite like this. What you will find is this. It's basically the same thing. Your controller, your resistor, your opto isolator, okay, safety ground, this is the LED, and instead of having a photo transistor, it will have a photo thyristor. So a photo thyristor is just another thyristor gate, okay, cathode, anode, gate, but the gate isn't electrically connected to anything. Shining a light on the gate turns it on, in the same way that shining a light on the base of this turns it on. And you would normally find that sort of circuit, and then this is used to drive your large thyristor, your power device, hot ground, and this is from your load live. Yeah? You'll find usually that sort of circuit, a resistor in here, and this goes to hot ground. The reason you find this is to do with switching this off, basically. If you use a photo transistor in here, you would have to make sure this was switched off to turn it off. Using a photo thyristor means you can send a pulse on the light into the LED, one pulse, the LED flashes, and you don't have to worry about this switching off. This will switch off when the main voltage passes through 0. This circuit will still have the zero crossing detection, so you will still have this here with a transistor usually in the opto isolator. This will still be there. 5 volts, safety ground, and the LED. So that will still be there, basically detecting the 0 voltage. This usually is an opto isolator which has a photo transistor inside it. So that, in a nutshell, pretty much is all you need to know about thyristors. These are the common circuits that you will see them in, with 1 or 2 opto isolators, or just something that's directly on mains voltage. And really, that is as complicated as they get. I'll just show you some thyristors. So these are low powered thyristors. The one I showed you on the data sheet, about 0.8 of an amp. This circuit is not isolated from the mains. I'll actually show you the circuit diagram for something like this so you understand how it works. And this is actually off a defunct set of Christmas lights, but we're going to have a play with this shortly and look at some waveforms hopefully on it. So those are thyristors. More commonly they are like this. This is a TO220. This is actually a Triac, but the thyristor looks the same. You may find in these sort of packages and similar things. So that's basically what they will look like. Sometimes they're in larger packages than this one if they're high powered thyristors. The way this type of circuit works then, because this is the other type of implementation you'll find thyristors. So in this case, the whole circuit is at mains voltage. This is your mains coming in, live and neutral, you'll see that these two are your load. In this case, it switches two loads, this one or this one. There are two thyristors, they can switch individually. And this, if you like, is your return from your load, which also happens to be the positive end of the LED. The other end of the thyristors, if your look comes to here, and this is hot ground. So I can basically draw this circuit how it is, and this is the other implementation will come. Normally in cheaper equipment, this is not as safe as the other ones because the whole thing runs on mains voltage. So in this type of device, we have AC coming in, 220 volts in my case, and this goes to a bridge rectifier. So the bridge rectifier, which is just a bit of diodes, basically 4 diodes. We have the 2 AC signals coming in, and we have plus and minus coming out. So this, as I drew before, this is an AC signal, and coming out, we don't have any smoothing capacitor on here. So what we actually have, this is your 0 volts. We have a half cycle, and then the other half cycle is turned upside down. Half cycle, other one up, as you've been turned upside down. So we get this pulsed DC, which is actually at twice the frequency of that. So if this is 50 hertz, because we're turning half the cycle upside down, it's no longer a sine wave, and it's running as 100 hertz. Okay, that's what the circuit does. So with this one, this is hot ground. By hot ground, it means it's connected to either the live or the neutral, alternately via the diodes and the bridge rectifier. So that's your hot ground. We then have, on ours, we have 2 thyristors, one like so, and this goes to one of the loads, which is a string of LEDs. And the other end of this goes to the other end of the bridge rectifier. And we have another one, exactly same thing. Load, which is another string of LEDs. The other thyristor. Hot ground. And we have a controller. A little microcontroller, yeah? Control. Okay? Now, on this circuit, the way the controller is powered is from this pulsed DC. We have a high value resistor, and that one then goes to a capacitor, electrolytic capacitor, and that goes to ground, and from here we go to the controller. And because this is a very high value resistor, I think on ours it says actually 150 kiloohms. The voltage here is low, very little current flows, and the controller no doubt has like a little Zener diode in, or some sort of regulator in that holds the voltage down here low. And it's about 5 volts, I've measured it. With respect to here, this is about 5 volts. But that's with respect to this point, which is hot ground. So in actual fact, there's a big AC signal on here, or rather a pulsed DC signal, and the 5 volts are just floating above it. Yeah, the 5 volts. This point is always 5 volts above that point. Okay, you measure the meter, you'll see 5 volts. You stick your finger on, you'll know full well it isn't 5 volts. Yeah, that's that. The controller then just effectively controls the 2 thyristors. There's no resistor in the circuit. I'm sure the resistor is somewhere on the little controller board. You can see here the controller is kind of like a little embedded thing in here. So that's what we have. And then we have the sensing for the AC, the 0 crossing, and in our case it actually is detecting directly from the AC coming in. So we have another resistor, 2 mega ohms, which connects to the AC. Okay, and that's how it works. So all this circuitry, as I say, is at high voltage if you stick your finger on it. But if you use your voltmeter from here to here, it's 5 volts. Don't let hot ground confuse you. It ain't safe for fingers. It's not finger safe, yeah? So that's the other sort of arrangement that you can find. Let's have a look now at Triacs and Diacs. Unfortunately now we know all about Thyristors or SCRs. We don't need to know very much more. So a Triac then. Basically it's just two Thyristors connected in anti-parallel. Anti-parallel means that they are opposite way round to each other. So we have one Thyristor, okay, gate, and we have another one wired the other way round, like so, and we have the gate of this one, which basically is connected to the gate of that one. So there are 3 terminals on our Triac. This is still called gate or G. These are usually either called A1 and A2, anode 1 and anode 2, or sometimes MT1, MT2, main terminal 1, main terminal 2. And all a Triac is 2 of these together. So now instead of only conducting in one direction, it conducts in both. Yeah. There's only a few things you need to know about these that are different from the Thyristor. They conduct in both directions, so they conduct the full AC cycle. Okay? We can turn them on or off with either a positive or a negative pulse. In this half cycle, to turn it on, you would send a positive pulse at the point you want to turn it on, and it will turn on and conduct for the rest of this half. When it passes 0, it will stop conducting. If you want to turn it on in this half, you can use a negative pulse, okay, and it will turn on. So that's really the difference between the two. The other thing that is notable is in this circuit, this one, where I used a diode to make sure only positive pulses got to here. With a Triac, you don't need a diode. Okay? Other differences. The symbol for a Thyristor, you know now, is this. Okay? Symbol for a Triac is this. Okay, bidirectional. And lastly, in this type of circuit where we used a photo Thyristor, to switch a Triac you use a photo Triac. So same thing internally, it will have the LED, but in this side it will have a Triac. The gate doesn't go to anywhere and it's photosensitive. Okay, like photo Triac, photo Thyristor. If you didn't use this, it would only switch on one half cycle. It's like a switched diode, but 2 of them back to back, and it conducts in both directions. The switching voltage is about the same. The switching current is about the same. The voltage drop across it is about the same. There's no other real difference. So what's the Diac? Yeah, Diacs you may not hear of so much. A Diac basically is like a Zener diode. If you know Zener diodes, with a Zener diode you use them in a reverse biased direction, like so. That's the symbol. And this will have a voltage rating, say 22 volts, and basically when 22 volts is reached here, it conducts. Yeah, and it maintains the voltage across it. So once the voltage here is high enough to put 22 volts there, this will turn on and hold the voltage. What a diac does, or is basically a bidirectional Zener diode. The symbol for a diac is really much the same as a triac, the only difference being that a diac only has two terminals. It's like a triac without a gate that automatically switches on at a certain voltage. So for example, 33 volts diac, when there's 32 volts across it in either direction, positive to negative, negative to positive, it will switch on and conduct. It will break that. And it will act like a triac. Once it's switched on, it will stay switched on until the main current goes away. That's what a diac is. They're used normally to switch triacs, and they look like diodes. So these are diacs. They don't have an anode or a cathode like a diode does, but they look sort of like a diode. They'll have a part number on them. I'm not sure if you can easily read this one, but the part number, basically, this is a DB3 diac, and the part number, if you look up the data sheet, will specify the breakdown voltage, if you like, the Zener voltage. So all a diac is basically a triac without a gate that switches on at a given voltage. Can we test triacs and thyristors using a multimeter? There's a good question. Well, let's try. So we have a thyristor, a low powered one. We have a triac, a high powered one. That's just what I happen to have. We can obviously test these with the component analyzer. So if you have a component analyzer, we can just connect the thyristor. Okay, I can switch this on, and it's saying sensitive or low power thyristor. It's telling us which pin is which. Okay, so we can test them with a component analyzer. Let's have a look at the triac as well while we're here. Sensitive or low power triac. So you can see it's calling them gate MT1 and MT2 there. We can test those. How about the diac? How about a diac? So we'll connect this to the analyzer, two wires, any two, and we'll try. And it's just saying there's nothing there. I do need to change the battery in this. That's not why it's saying there's nothing there. What if you don't have a component analyzer, but you still need to test the thyristor? Okay, let's try it. It's easiest to do this with a few crocodile clip leads. So on this one, this pin is the cathode. Okay, this pin is the anode, and the one in the middle is the gate. Let's attach 3 wires. Okay, now I'll put my meter onto diode mode, and if it's a good thyristor, it shouldn't conduct. The switchable diode is switched off. Now let's try to switch it on. So if we connect the gate to the cathode, it's switched on, and it will stay switched on now until we effectively short out the circuit to stop the current flowing through it. It switches off again, touch it again, it will switch on again. Yeah, switched off again. So we know that is basically a good thyristor. Obviously you can test them with a higher current under load. They can fail under load or break down, but that's a pretty good indication we have a good thyristor there. Let's have a look at a triac now with a multimeter. So on this one, this is the gate terminal, and these are the anode 1 and 2, or MT1 and 2. This being a bidirectional device, it will conduct current in both directions. So first we will connect our meter across the main terminals in this direction. Just get a good clip on it. Okay, it's on. And we'll attach the white wire again to the gate. Now, it should switch on when I connect it one or the other of these. Yeah, that's switching it on. You notice this one isn't latching because it's a higher powered device. The threshold current must be higher. You could make it latch, but you'd have to use something like a little power supply battery and LED. Give it more current if you wanted to test it that way, okay? When you go to the other one, nothing happens. So only connecting to this main terminal will it switch on. Now let's reverse the wires. So the gate stays where it is. And we'll reverse the polarity of these two. Okay? Now what happens? While it's now switching on, effectively when I'm on the red wire, yeah, the green wire isn't, so it's reversed. Okay? Before I was touching the green wire on this terminal, switch it on. Now I'm touching the red wire. So that's a pretty good test for a Triac. As I say, you could make a circuit something like this on a bit of breadboard, quite simple. 0 volts, LED, resistor, some voltage, and make sure enough current flows through to latch it. If you're doing this, you'll have to put a resistor also in with the gate, because using my multimeter, it is a constant current source. You don't want too much current going to the gate, but if you do something like that, you can now switch it on by putting the voltage onto the gate. Yeah. So it is possible to make little circuits to test them, but if you ask me, that does the job just fine. As usual, it's normally easier to show you something than explain it to you. So this is my bench power supply. This is a dual supply. I can use it independently as 2 separate supplies. I can have it in parallel to give me 30 volts at 6 amps, or I can put them in series to give me 60 volts at 3 amps, and I have it in series. The power supply is connected via a resistor. I've used a 390 ohm. The value isn't that important. That's connected to the Diac, and that's connected back to the power supply. And these 2 leads just go to my test meter, positive and negative. And I'm measuring the voltage across the Diac. So I'll increase the voltage on my supply. Now you'll notice that this is reading 4.5, 4.5, and this says 9. So the output voltage is the sum of the 2. Yeah. If, for example, we go up to 10 on here, that will give us 20 volts. Yeah. This Diac is a 33 volt Diac, I think. So basically nothing will happen. The voltage here will match the voltage coming out of the power supply until we reach about 33 volts. Yeah, we have 30 volts now, 15 and 50, and let's go up a little bit more. 32. And it triggered, yeah? Watch again. Yeah, the current meters are saying no current flowing on here as well, until I get a voltage up here, and then the Diac will switch on anytime now. Okay, it's 35 volt, yeah, and this is now drawing about 8 milliamps, 4 and 4, you can see on there. Okay, so that's how to test a Diac. I've now connected the little PCB to a light bulb. The light bulb is 65 watt. The rating for this thyristor was half amp continuous, which on the 220 volt is about 110 watts. So it's more than capable of driving the lamp. I've connected the handheld oscilloscope, so this is not connected to anything, it's completely isolated from the mains, and this is important, otherwise you can't do what I'm doing. I've connected ground of the oscilloscope to hot ground on the PCB, and I attached the probe to the gate of the thyristor. So let's switch this on and let's see what this is actually doing. So we switch it on, you can probably see the bulb flashing or the light from it. And you can see there the waveform that is being driven. I can go to single mode and we can just actually have a look. You can see this is the drive and you can see that it's switching on part way through the cycle. Switch it back on again, it's running again through the various different widths of it as it is flashing. Yeah, you can see it starts flashing faster. So that's what is actually happening on the gate. I've switched it off now. The capacitor is discharging, it's going away. I can also look at the actual voltage going into the light bulb. So we'll just turn this upside down. If you have a look, you will see this is hot ground and effectively connects to this end of the thyristor. So the red wire is going to the light bulb and the other end of the light bulb comes back to the other end of the mains, or rather the other end of the bridge rectifier. Okay, I've now attached the scope probe to the signal, which is effectively going directly to the light bulb. You can see there, so it's now going to full brightness and then off again. That's what you're actually having. It's going through the various brightnesses. It's now, if you like, doing the other bulb, the one I haven't got connected. This one's driving again, yeah? So you can see. Okay? So that's basically the sort of waveforms you'll find on a thyristor. Just a word of caution. Beware when you're doing this sort of thing, even with a handheld scope like this. The metal part of the BNC connector will be connected to hot ground. This will have a high voltage on, and you will certainly notice if you put your fingers on it. It's no more dangerous than working on things like this or working on power supplies. It's just a matter of understanding the risks. If you understand the risks, this is relatively safe if you know what you're doing and you know what not to do. If you don't, then really I would suggest you don't try to work on this sort of equipment until you thoroughly understand the principle of ground and hot ground. If this video is really going to be all you need to know about thyristors to fix stuff, then we just need to talk about what goes wrong with them. Normally speaking, if a thyristor fails, it goes short circuit. They may go open circuit, but short is what normally happens with them. And the main thing you need to consider is, if a thyristor or triac goes short, almost certainly it's because whatever load is attached to it, whatever it is switching, was also short. Therefore, it switched on, feeding into a short, it passed too much current, and it went blue, yeah? Sometimes they can actually explode, in which case they are definitely open circuit. That is basically what you find with thyristors. If they are not opto-isolated from the low voltage circuit, then if they do explode or go short, they can damage the driving controller in this sort of circuit. If they are connected to an opto-isolator in this sort of arrangement, if the thyristor or triac has blown up or gone short, then you need to check the opto-isolator as well. But the damage can't go any further back than that. You may find tracks blown off the board as well. So generally those are the only faults you'll find with these components. They don't go lazy, if you like, whereby they lose their sensitivity, the amount of current or voltage needed to turn them on. But what you can find is a situation where somebody else has tried to repair an item and the thyristors or triacs have been replaced with the wrong type, which are not sensitive enough. You would normally know that because, as I was just doing with the handheld oscilloscope, and by the way, do not try that with a bench oscilloscope unless you understand grounding and ideally have an isolation transformer on your bench. You need a handheld scope for this type of work. If you can see on the handheld scope that there is drive getting to the gate but it's just not switching on, it's possible that somebody's replaced them with the wrong type, or that you have replaced them and the type you fitted are not sensitive enough, they're the wrong type. I've done that myself a long time ago in the 70s and had to eventually call the tech support, who were very nice and explained to me what the problem was. You can usually also see that the thyristor is turning on with a voltmeter. So if you measure from the cathode to the gate, you'll probably see like a little bit of a varying voltage. If it's something like that was flashing, you can just see like a little bit of varying voltage. I won't show you on this video, but I will link the one where I was trying to repair those Christmas lights, where that PCB came from. And if you watch that through, you'll see exactly how it looks on a digital voltmeter and volts range, and how I actually knew that the thyristors were switching. Okay, so that I will link at the end of this video and in the description. Really then, guys, that is all you need to know about the thyristors to fix stuff. I hope you enjoyed that video, found it an hour well worth investing in your own experience and knowledge, and I will see you all soon on another linear electronics repair video. Ciao for now, guys.